Okay, thank you everyone for attending my talk. So today I'm going to talk about uh, our recent work, which is accepted by OUT this year. This work is about the linear reinforcement learning with ball action space. This is a joint work with Zeyu Jia and Zhu Madaka and Dean Foster. And here, in the middle of the slide, actually this is the link to our paper, and anyone who's interested in this topic, feel free to go through this paper. Yeah. So let's get started with some Markov decision process recap. Since everyone here is from the RL theory community, so this is a really common knowledge for us. So first we consider the Markov decision process, where S is the state space, A is the action space, and P is the transition model, and also the reward, and also the we consider the finite horizon MDP, which is of the horizon edge, and we assume the start state or initial state to be S0. And we assume that for any policy pi, this Q function and value function are defined here. Like actually is the expected, or here, we miss the expectation here. So it's the expected of the rewards, and the value function is also the expected of the rewards. And here, according to this value function and Q function, we can define this this optimal policy pi star to be the maximum maximum policy such that this V pi S0 attains its maximum. And our objective is to find a policy pi which is very close to this pi whose value function is very close to this pi star, the optimal value function. So actually, in this Markov decision process, if we do not put any restrictions, there exist some algorithms that can achieve that can make us learn this problem. But actually, these algorithms will scale with the number of states and number of actions, which is normally very large, such as in the AlphaGo, this or maybe in the Go setting, the number of states is exactly 3 to the 361. And also in the self-driving, actually the number of states is infinity. So if we do not put any restrictions, this problem is intractable, even if we have some guarantees, like actually depending on the number of states or the number of actions. Yeah. So here we make a very normal assumptions where we call it linear Q star assumption. This assumption is actually used in the approximation in the function approximations, linear function approximations in reinforcement learning very generally. We only assume that the Q star, the optimal Q function, can be written as a inner product between the features of any state action pair and also parameter theta star. And here we assume that this theta star is different across different layers. So at layer 1, this is theta 1 star, and at layer capital H, there's a theta capital H star. And this assumption, linear Q star, this assumption is that we only assume that this Q star assumption, this Q star is linear parameterized. So this is a really weak assumption, and it's really useful. As you can see that if we consider maybe the deep Q network, actually the neural network actually learns some features, and we use these features to make predictions on the Q star function. That is so this deep Q network actually it will fall into these categories. So we can write this Q star as the inner product between the feature and also some theta star. Yeah, actually we skip the process of learning the features, and we assume that the features are given to us. So this is the very common assumptions where we call it linear Q star. So even though that this assumption is well known and widely used in the theory or the practice, but actually if we only assume that this assumption, there's no algorithms can be polynomial. So this is some previous papers by Chaba, they prove that only with this linear Q star, this problem is essentially hard, is exponentially hard. But actually, apart from this linear Q star, if we add some additional assumptions to this problem problem might be tractable. So the one of the most common assumption is the linear transition and reward assumption. That this assumption assumes that the transitions, this P S prime over S comma A can be written as a inner product between phi S A and also psi S prime. So and also the reward RSA can also be written as the inner product between the phi SA and also some theta. So this assumption, actually, we make some assumptions on the models. Given these assumptions, there is a bunch of polynomial algorithms in the previous literatures. There's a lot of such literatures, so I do not list them here. But this is a really useful model. But one problem of this model is that the assumption is too strong.
Can I just ask a clarification quickly? So when you talk about polynomial algorithm and exponential hardness, what do you exactly mean? Is it compute or sample complexity?
Oh, this polynomial. Oh, I mean this in the whole talk, actually, what I talk about here is the polynomial means the sample complexity, not the computational complexity.
Okay.
Yeah, I agree that the computational complexity is also an important question, but here it's not in our topics in this talk. Yeah. So all of this, these poly algorithms are exponentially hard. This means that there exists poly sample complexity algorithms, or the problems cannot be solved by polynomial samples, or these problems has to be solved by exponential number of samples. Yeah. And this linear transition and reward, even though that we know that there exists some algorithms, but this problem actually is very restrictive, because actually sometimes in the real world we cannot model the transitions or reward. The only thing we can model is the value functions, because if we just put the deep neural network maybe in learning the Q star, the only thing that we can guarantee is on the Q star functions. There's no guarantee on the transitions or reward. So this linear Q star problems, whether we can make it to be tractable, this is a very important research direction. So given this, there's a lot of works that can make this problem tractable. Like here, in the third row, there's a paper shows that if we only assume the linear Q star, and we also assume that the problem is with constant gap, and if we have access to this generative model that is given the state action pair, we can query the next state and the reward according to this state action pair. Then there exists a polynomial sample complexity algorithm. Yeah, this is one result. There's also results showing that if we assume that the V star assumption is the V star function is linear parameterized, and plus the assumption that there's only constant number of actions, there exists a polynomial algorithm. And also there's also a previous work showing that if we assume that both the Q star and V star, these two functions are all linear, then we have a polynomial algorithm. So here in our work, we make one step further, studying on what additional assumptions we make on the linear Q star assumptions. Can we make this problem tractable? Yeah. So this assumption is what we call the Ball structure action space. So let's first mention why we consider this Ball structure action space. Actually, why we consider this this assumption is that actually many decision-making problem has a Ball structure space. Action space, such as actually maybe if we fighting monsters or digging treasures or maybe driving cars or maybe doing some navigations, everything that we encounter is that actually we can query all of these directions in the model. So one common assumption survey can make is that this ball structure action space. So this is a really common this is a really common assumptions used in practice. And right now we study whether if we add these assumptions into our model, so whether this problem can be tractable or not. Yeah. So any questions on this?
Yeah, you do seem to have a question. Do you want to read out your question? Vishal.
Yeah, so by polynomial or exponential, do you mean computational complexity? I'm repeating this question, but.
Oh, so you're considering whether this our algorithms can be solved maybe in within computational polynomials computational complexity, right?
Yeah.
Yeah, actually, we haven't studied this problem before, but we believe that actually this algorithms that we implement is it will have some polynomial computational complexity. Yeah, but actually one thing is that one thing is very hard is that actually in our problems actually because we assume that we have access to all the features phi, and actually this features phi can be infinite. So if we consider the computational complexity of this problem, so maybe just enumerating over all these features, this will become an intractable problem. But actually, I think that this can be solved by adding a proper maybe oracles or maybe computational oracles, so that actually we can compute these problems in polynomial computational time. Yeah, but that's something outside this topic. But actually that's a very interesting question that we that is I think maybe what oracles can we add to this maybe models can we make this problem computationally tractable? But here, yeah, since actually this statistical problems, I mean, the sum complexity problem is already interesting enough, so we only focus on this sum complexity here.
Cool. Okay. Thank you.
Yeah, so here we make the formal definition of this ball structure action space. This assumption is that for any state S, we assume that this phi is a ball. So this is a really straightforward assumption, right? So given a state, if we consider the actions around this state, the actions, the features of these state action pairs forms a ball. So this is the assumption we make. But this assumption somehow is a little bit intractable for us to analyze. So we make the following simplifications to this assumption. That is, we assume that this there exists this phi and also this radius rho, such that this this phi SA, this set is can be written as the phi s plus this this ball of radius rho s. Yeah, and actually one further simplification that we can make is that we can assume that this phi s comma a equals to phi s plus a. That is because we can just rearrange the actions so that actually every actions maps to the exactly this phi s comma a minus phi s. And actually this step, as I mentioned before, that this step can be computationally intractable if we do not have a proper oracle. Yeah, because actually since we are only given this feature space, so maybe only enumerating over all of these infinite features, this is computationally intractable. But actually, as I said, if we give a proper oracles to this problem, maybe this can become a computational tractable problem. Yeah, and actually note here that this phi SA, that this mapping A to the phi s comma a minus phi s, we don't require this to be a one-to-one mapping. Actually, we can have many actions mapping to the same thing. And actually, in that case, actually, there's not much difference in choosing these actions, because actually, if one action is optimal, then because we have this linear Q star assumption, we know that the other actions that maps to the same thing, the action that maps to the same thing, that action is also optimal. So so it's no matter we choose these actions among here, so this is always the optimal policy.
Yeah, so I had related questions about both of these assumptions. So first, you started to make this assumption that, so you said something about that dealing with directly with assuming that the phi feature map gives you a ball is intractable or too difficult or something like that. And then you made the assumption that that is the phi. So it's the separability assumption that is the phi s plus the other component, a ball. And then you're making a third step, and here you're saying,
Actually, the
yeah,
first step actually is only the making the notations to be clear, because here our assumption is that this phi is a ball. So given that this is a ball, he must have a center and also a radius. So this phi s and the rho s is that we clarify what is the radius and which is the center. And the second,
okay, so that kind of like implicitly, okay. So computationally, if you were given just an oracle that can query what the features, then maybe you can construct the center approximately very quickly and the radius approximately very quickly, and you would have this information at your disposal anyway. So you're saying that these you can assume without loss of generality in this sense. Is that correct?
I'm not sure. Yeah, I think that yeah, if we just use this phi to maybe approximate this state and actions, this I mean this
Might break things. Who knows?
yeah, am I understanding correctly? So you mean
Yeah,
that we can use this phi as comma a? Given this phi, we can maybe query some of the state and action pair. Given a state, query some of the actions, so we can approximate this phi s and also rho s.
that's right.
So
Like
this
approximating the
make the problems computationally tractable. Is this a problem? Is this a question?
Yeah, the question is whether the approximation error that will be introduced in this process, because you don't have infinite compute, is going to be an issue later or not?
I think this will not be an issue in the problem, because actually our algorithms allow some small maybe misspecification or yeah, it's somehow robust.
Okay, and then there is the other aspect of the question, which is on the next slide, but maybe I first let Armand ask his question because he seems to have a question.
Just very quickly, are there many settings where this assumption holds?
Yeah, actually, this assumptions yeah, actually, there's some maybe imaginations of settings, because this is only one steps we make towards to solve the maybe the reinforcement learning problem. So actually, if you think about maybe if we maybe attacking a monster, like actually a monster is in this area, and actually we can maybe attack it here or here or here, and actually if we maybe attack it in the right place, it will maybe make a large impact. But actually, if we attack in the wrong place, then actually this will be no impact or not. So actually, according to this, we can assume that actually the monster here actually create some of the ball structure action feature space, so that actually if we attack in some directions, it will we can write the number of impact actually as features, and also the some unknown theta. So that is why we assume that this assumption holds. So actually, I know that I agree that in the real world the setting is much more complicated, but actually making this assumption, like actually for every state this feature space is a ball, actually it can help us understanding that help us understand in which settings, or maybe under what circumstances, maybe we can find polynomial algorithms, or maybe find tractable algorithms to solve it.
And just quickly, does the ball depend? I mean, a ball depends on a norm or a distance. So is the choice crucial for what you're going to be doing or not?
Yeah, this norm. I think that right now we only consider the Euclidean norm, but I think that this norm can be also generalized to some maybe some more complicated norm. Yeah, this generalization is this can be done, even though it's not very straightforward. But I think with some technique we can do it.
All right, thank you.
I would be worried about the L infinity norm.
Our infinity norm actually, if we don't assume that this D is very large, so this our infinity norm is very similar to the ball structure. It's to the Euclidean.
Okay,
So actually,
let's see.
Yeah,
Okay.
so actually these two norm actually somehow maybe is nearly the same. So if we can solve it in the Euclidean norm, we can maybe pay on additional D factors, so that actually we can also solve our infinity, or maybe even our one norm. That's also doable.
Right. I was just thinking that the L infinity ball has a lot of corners.
Yeah. This our infinity ball is very useful. Yeah. Actually, later, actually we'll show that this algorithms not only hold for ball structure. Actually, we can also assume that this this ball is a convex set. But actually, if all of these convex sets are similar to each other, we can also do it. So if we just take the convex set to be the cube, so this will corresponding to our infinity norm.
And you are not bothered by how many corners it has.
No, actually, the number of corners actually doesn't affect our rate.
It's not pointy enough to be worried about it.
Yeah, actually, this why poly D additional poly D factor is enough is actually for a cube. Actually, we can consider a ball which is contained in this cube, and also a ball that contains this cube. These two balls, actually, the radius is only of the D factors difference.
I see.
So if we just exploring using the outer ball and actually using the inner balls for some exploitation, so we can pay additional D factors so that we can achieve the same bound.
Yeah. Got it. Okay. And then there was the second part of the assumption, which basically was introducing this separability structure. And there, I guess once you have this ball, I guess you will want to carry a certain direction in the ball, and you would need to have an ability to translate that direction into an action. So that's kind of the hidden assumption here, right?
Yeah.
That you have access to that. Okay, got it.
Yeah, so here, this assumption, actually, if we want to achieve the computationally efficient, we have to assume that given maybe a phi as A, we can find the action A in the action space, so that this action corresponds to the phi as A.
Gotcha.
Yeah. Okay. Got it.
Thanks.
Yeah. So I shall move on. So here in the following, actually, we assume that these two assumptions hold. So this phi as A can be written as phi s plus A. And also, actually, we consider the online learning setting, but actually, we can assume that actually our algorithms work for assumptions that's even weaker than the online learning. The online learning actually can give us the full information of the trajectories from the first state to the states in the horizon edge. But here, it turns out that only the total rewards, sum of h equals to 1 to capital H, this reward, and also the radius of each state. Only these two pieces of information will be enough to us. So this is even weaker than the trajectory learning or online learning. So to introduce the algorithms, let's first do some warm-up. The warm-up is a very simple setting. Like actually, if we assume that this rho sh are identical for all the states in the layer H, so if we assume this, so we can assume that for any states in the layer H, in the state space sh, all of the radius equals to the rho H. So if we assume this, and further we assume the boundary rewards, we show that there exists a very simple algorithms that can learn this. So to introduce these algorithms, let's first look at the Bellman equation. So we can write the Bellman equation in this way. Like actually the theta star interpolate between phi at layer H can be written as the expected of the these following things, also condition on SH and AH. And if we write out this feature phi, it comes out in the following way. Because we know that the feature phi s comma a can be written as a phi s plus a, so we can obtain this following equation. So this means that the interpolate between theta h star, also phi sh plus ah, can be written as the expected of the reward plus the expected of the next state, this phi h plus 1 star, and also theta h plus 1 star on the phi sh plus 1, plus this rho h plus 1 times the norm of theta h plus 1 star. So given this equation is very useful in the construction of our algorithms. We can telescope these equations from the first h equals to 1 to capital H. And if we take the expectation in the over all the trajectories, we can obtain this following equations. That is the expected of the phi s1 and also theta 1 star plus this expected of the ah and the theta h star is exactly this expected of the total rewards plus this expected this sum of the radius times the theta h plus 1 star norm, true norm.
Sorry, you went quite fast on the previous slide. Could I just get you to back up a little bit and tell me where that supremum went?
Oh, this supreme actually is becomes this term. Yeah, that is because this a as we assume that the action space is exactly this ball.
Right, so it's the norm.
Yeah, so if we just take the supreme here, yeah, actually this becomes a true norm. Yeah, the Euclidean norm of this theta h plus 1 star.
Right, thank you. That explains it.
Yeah. Yeah, and given this equation, and actually, so we can have the following thing. We can evaluate this theta h star, also the interpolate of rho h times the s unit vectors can be written as the difference between two expected total rewards according to two different policies, where this pi hi is that the policies that take action zeros outside the layer H and take action rho h ei in layer H.
So just to back up a little bit. So here we fixed the policy, then we were rolling out with the policy that generated this AH and all the expectations with respect to that. Is that correct?
Yeah, actually this expectation is over the policies. Given the policy pi, and actually the policy pi will maybe if we at state s we give action pi s there. So this expectation is over all the trajectories that samples according to this exactly this policy. So
okay, all right.
Yeah, like take the example of pi 0. So pi 0 means that actually at every state we take action 0. So starting from the initial state, and actually if we take action 0, transit to some other state, there's maybe a transition here, and if we transit to some state s1, we also take action 0, transit to x2, and so on. Yeah, I saw there's a question asking about this. What is I? So I here is the ith dimension of this. Yeah, we assume that there's a d dimension. So we evaluate this theta h star in the dimensions from the first dimension to these dimensions one by one.
So then I was asking what's pi hi?
Mm-hmm.
What was that?
Yeah, this pi hi actually is defined here. So this pi hi is that it takes action 0 for every horizon or every layer is not h, and take action ei rho h. Oh, here there's a should be rho h ei at the layer h. So actually we explore only at the layer h on the direction of ei.
Ah.
Yeah.
Rho h ei.
Yeah.
I see. Okay.
Yeah. So based on this,
can you go back to the previous slide? I think we need a little bit more time to process the previous equation. So basically, what was happening from the telescoping? So let's say we believe that this telescoping works out. That seems to be believable to me. Then what was happening after that?
So you mean after this telescoping?
Yeah.
Yeah. We noticed that the first state actually is all the same across all. No matter the policies we choose, this term is always the same.
Okay, and
the last term actually is also independent to the policy we choose.
Okay, so then we take two policies and then we subtract the two equations from each other.
Yeah. So if we subtract this equations with respect to pi hi and also this equation with respect to pi 0, we notice that the left-hand side is exactly this term.
So pi 0 is really the policy.
Pi 0 will give this term
actions.
0. Yeah, because h is always 0.
So we have this very interesting or weird policy space where we can just like set the actions to 0 and then kind of nice things are happening because of that.
Yeah, exactly. Yeah. This I think that the most important property we used in the ball structure action space is that in the ball structure we can explore in every direction. Like actually, if this direction is very good, I mean these directions can maybe separate theta hi from all of other theta and all of other components. Then actually we can just query these actions to learn about this theta hi. So because the ball actually is actually we can take any actions.
I see what you mean. Like basically on the left hand side, we are querying the ice coordinate of theta h star.
Yeah.
Up to accuracy or like this rho h scaling, right?
Yeah.
And on the right hand side, we can roll out with the policies and just measure these differences precisely as you want.
Yeah.
And then you get the ice coordinate and you can just like, because of the structure of this problem, you can query the coordinates of the parameter and the unknown parameter vector one by one. Very cool.
Yeah, but actually, one interesting question starting from here is that this algorithm only achieves 1 over epsilon squared. If we translate this into the regret setting, you will get a t to the 2/3. So this is not optimal. So actually, or it's not optimal as we guessed, because we guessed that the optimal thing should be root t. Because as you can see that if the h equals to 1, this is exactly the linear bandit with the action supposed to be the ball. So we should get a root t of to be the optimal regret. And now that actually, given that this horizon h doesn't have a exponential influence on the pack bond, so we can also conjecture that this layer h doesn't influence the regret bond as well. So we conjecture that there exists a root t of the root t regret algorithms, but we cannot. So far we haven't proved the thing. we connect that this is true.
Yeah. I see.
So to get this root T, actually we cannot do this naive explorations. Actually, we have to balance the exploration and the exploitation more carefully. Actually, because actually, if we just naively query this rho H EI, it can induce some very large regret. So this is unacceptable in our setting.
Mm-hmm.
Yeah. Yeah, but here, just to demonstrate that this is the idea of this algorithms, actually, we just query this action EI. This is just a very good start. Yeah, also, one other thing I want to mention for these algorithms is that if we notice that in this equation, actually the left-hand side is the inner product between rho H EI and also theta H star. So sometimes if we encounter some very small rho H, that means that we cannot evaluate this theta H star very accurately, right?
Yeah.
Yeah. But actually in our theorems we can show that actually even if that we even if when rho H is small, we don't have a very accurate estimation for this theta H star. But actually this accuracy doesn't influence the final Pike bound or the final accuracies a lot. That is because actually if rho H is small, that also means that no matter actions we take, actually the actions will not make a huge difference. So if we just take this action or take that actions, so it will nearly performs the same.
Can you just say that you are scaling all these balls so that they have a unit radius and then put the scaling into the theta H star?
Yeah, actually, we have been thinking about this rescaling this ball, but actually, this somehow turns to be a little bit intractable. That is because actually, if we only consider the total rewards, because we only have this linear Q star. So this linear Q star actually is the sum over all of the rewards across layers. So if we do this rescaling, it will break this balance because actually maybe we'll put more weights on the first layer and less weights in the second layer. So this is not the thing that we wanted to happen.
Okay, got it.
Yeah, but actually, in the proof, actually, to balance this rho H EI, this rho H and the accuracy of theta H star, this is also one thing that we show that this is a very good balance, even if we don't redo some rescaling. There's still good balance.
Good.
Yeah. So this is our algorithms. So it's very clear from the previous analysis. So we first query pi 0 and then we query this pi hi. And we collect arm trajectories with respect to these two policies. And we just make the difference, calculate the difference. And we just take the grade and we just calculate the approximate theta H star and also the gradient actions AH. And we output this pi SH equals to AH. And our algorithm shows that if we choose to be polynomial in H and D, and F also 1 over epsilon, so this algorithm with high probability will output the epsilon optimal policy. And the total number of samples is polynomial as it's shown here. So any questions so far? Okay, yeah. So I shall move on. So given this ball structure, we can also generalize this to the convex action set. So the convex action set is that we assume that actually we cannot do this for any possible action set because we have to do some explorations in all the directions. So we assume that this we make the assumption of this regular convex set. That is that actually it can it contains a ball of radius rho, and also it is contained by a ball of radius eta. And if eta over rho is equals to b, we call this as a regular convex set. And actually, there are some examples. Like actually, ball is definitely a one regular convex set, And as I mentioned before, this d-dimensional cube is also a regular convex set with a parameter root d. And also the ellipsoid is also a A or B regular convex set if A and B is the longest and the shortest principal axis. So given this assumption of regular convex set, we can deal with some more complicated norm. Like actually the L1 norm or L infinity norm, these samples are all covered here. So assuming that this action set is always the B convex set, B regular convex set, we can show that also a polynomial sample complexity algorithms with an additional B squared in the sample complexity bound. So the proof of this theorem is very similar to the previous one. Actually, we only uses the rho HEI as a exploration, and the exploitation term is eta HEI. And if the radius between, if we know that the ratio between these two is exactly B, so we can use an additional B squared to bound the error. So this is the simple generalization to the convex ball. So this is so right now in the next, let's come to the main part. That is the action set with a different radius. This is just the original setting, because actually we just dropped this assumption of rho sh equals to rho h. So we only assume that rho for every sh, there's a Ball structure of rho of the radius rho sh. So why is this problem harder than the previous one? Yeah, in the previous one, actually we assume that every state in the same layers actually are of the same radius. So if they're of the same radius, that means that if we encounter the states maybe in the layer H, we can we know that the radius is all the same, so we can just query this the action rho HEI, and we know that for all the states here in the layer H, the exploration radius or the exploitation radius actually are all the same. So this doesn't bother us in the algorithms. But actually, if we just drop these assumptions, maybe the problems looks like is in the right figure. Yeah, like actually for some states there's a very huge ball, and for some other states there's a really small ball. So for this setting, like actually one thing will become more trickier is that if we do while we're doing explorations, all the things that we encounter are all the small balls. But actually for the exploitation part, if we do the exploitation, we all met these larger balls. So if that's the case, because actually the small balls will give us inaccurate estimation of the theta h star. So if we just use this inaccurate estimation to do exploitation in the larger balls, this will give us a very large errors in the estimation. So that's what we don't want to. So how do we solve this? How do we solve this? So actually we just classify these states into two parts. The first part is that the larger rho s can make the problem easy to learn, and also the small rho s can make the means that taking any actions won't matter very much. So this can give us some ideas to balance the exploration and exploitation. That is, if we encounter some if the radius we encounter are all the larger s, that means that we can do the exploration very well. And actually, if we have a very good exploration, that means that we have a very accurate estimation on the theta h star. That means that if we do exploitation, that will also gives a good results. On the other hand, if the states we encounter are all the small radius, that means that actually we cannot do the exploration very well. But actually, if we always encounter the small radius, that means that the exploitation is very easy, because we can take arbitrary actions. Actually, it will also give a good results. So this is how we deal with this problem. So, but here we have to make an additional assumption, that is all the norm of this parameters theta1 star to theta h star are all the same. Yeah, actually, this assumption is also very common in some previous literatures, where we assume that theta1 star to theta h star are all the same. If we assume that they are all the same, then their norm are definitely the same thing. Yeah. And also, how to drop this assumption is also one interesting future research direction. And as before, we assume that the bounded total rewards, that the reward is between 0 and 1. And also, we make a very common assumption, like actually that along any trajectories, the sum of the radius is also bounded. Yeah, because we can always scale the radius. So this actually scale the radius simultaneously. So we can always scale the radius so that they are bounded like this. Yeah. So right now, let's talk about how these algorithms construct. So because we assume that the theta1 star to theta h stars are all the same, we can do some grid search on this capital theta. Yeah, because actually this similar to the previous analysis, we can also write this formula, like actually this phi s1 theta1 star, this inner product plus this expected under positive pi of this sum of A and the inner product between A and theta star is equals exactly the expected of the total rewards plus theta times the expected of total radius. Yeah, actually, this term is different from the previous analysis because in the previous analysis, taking any actions will give the same total radius. So it doesn't matter what this term is because it will always cancels out. But here, this setting is different because the radius can vary across different trajectories. So this theta has 2 times of the expected of the total radius. And actually, our idea to learn this problem is that we want to make this last term goes to 0. So how do we do this? So we'll just use the grid search to search what the exact value of theta to be. And if we actually if we search the approximate the right theta or very close to the true capital theta, this term will be a very close to the true estimation. So in that case, actually we can prove that the policies we return is very close to the optimum policy. So finally, because there's only 1 over absolute number of such grids, so we just run each of these policies calculated according to some one of these grids individually, and then we can just find the policies with the largest reward. We can show that this policy is very close to the optimal policy. So this is the part that's different from previous. And another very interesting ideas we introduced in this work, this algorithms, is that what we call the hierarchical exploration. And the previous setting, if we assume all the radius are all the same, so we only need to do 1 layer exploration. That'll be enough because actually this last term will cancel out. But here, this last term it will not cancel out. So actually, how do we achieve the most efficient thing here? So actually, we just quickly query some policies and find out that what is the exact value of this thing. And actually, if we encounter the policies where this expected of the total radius is larger than 2 times of the previous estimation, that means that actually our previous estimation is not accurate enough. So we can just replace the current policies and use the current policies to do the explorations once again. Yeah, and I actually every time we just repeating this, actually will grow this expected of the total radius 2 times larger than the previous estimation. So we can show that with only log 1 over absolute number of hierarchy, we can get an accurate enough estimation here. And the last building block of the algorithms is actually we ignore the small radius. Yeah, this is also discussed before. Like actually, if the expected of the total radius is small at layer h, then whatever actions we choose in that level will never make a big difference. So we can just ignore this action we make in that level. We can just pick a random action there, and actually it never bothers us in the algorithm. So these are all the building blocks of our algorithms. So according to this, we can construct the following algorithms. That is, we mark this each exploration policies for each step. So initially, we'll just choose it randomly, maybe also this pi hi stuff. And then we sample m trajectories according to the exploration, each of these exploration policies. And next, we just approximate this capital theta by the grid of this L times epsilon. And we calculate the estimation of theta 1 hat to theta h hat. And in the next, we just find the best gradient policies with respect to this choice of L. And in the last step, we check whether these policies satisfy the for any layers. For any layers, this expected of the total radius is less than the radius is less than 2 times of the expected radius of the policies we used to explore. And actually, if this doesn't, if this inequalities doesn't hold, then we just switch the exploration policies to this gradient policies we calculate, because according to this equation inequality, we know that this policy pi will give us the better explorations here. So we just repeat this process until for any h this inequality holds, and at that time we stop our algorithm and just output this policy pi. And given these algorithms, we have the following theorem showing that if we assume that all of this theta h star, the norm are all equals to capital theta, which is less than 1, and also the bounded radius and bounded reward assumption, these algorithms will output the optimal policies using this h to the 5th d cubes over absolute cube number of trajectories. So any questions for this?
Really on questions, but I think we let you finish.
Yeah. So I think I'm also run out of time, so I just finish here. So this is everything about this talk. So the first we investigate on the linear Q star problems where the action space has a Bose structure, and under certain assumptions we prove the existence of the polynomial algorithms, polynomial samples complexity algorithm. And also, in the proof of different radial cases, we make the assumptions that this theta 1 star and to theta h capital H star are all the norm are all the same. So how to drop these assumptions is the interesting future research directions. And also, as mentioned before, the computation under what oracles can we achieve the computationally efficient algorithms? That is also one interesting future research directions. Yeah, and that's all about my talk. Yeah, thank you very much.
Thanks, Zeyu. Please go ahead with questions, guys. Raul?
So the state space is assumed to be compact, is it?
The state space, yeah, actually we don't have restrictions on the state space. It can be discrete, but to be compact, yeah, actually we assume that the features are all bounded.
I see.
So if the features are all bounded, so we have this compact assumptions. That's also.
I mean, like, you don't have an assumption on the state space per se, right? You don't need anything for that.
It's
happening in the feature space.
Yeah. Actually, the state space actually can lies whatever it is. It can lies maybe here, here, and also infinity. That doesn't matter. The only thing which matters is that it can map the infinite states at the infinite further to the maybe in the compact space of the features. That's important.
I see. And the episodic, so this was episodic setup, correct? So do you think extensions to non-episodic RL would be interesting?
So you mean this discounted MDP setting?
Or average, maybe? Average cost setup or cumulative?
Yeah, that's also interesting. But I think that this if we just consider the maybe discounted case, if all of the for the discounted case, there's only one theta. So if we can evaluate this theta very accurately, then actually this problem is solved. So for the discounted case, I think the problem will become easier. For this episodic setting, actually we have a number of layers of the parameters, so we have to do more things about this layer stuff. But for maybe the average reward cases or the discounted cases, that's I think this current algorithms will directly generalize to that setting, and the analysis will be easier than this one.
I see. Thanks.
I was wondering if you have a pseudocodes of the big algorithm for the non-uniform row case.
Actually, that's in our paper. Yeah, actually, I can show you. Yeah, I can show you.
Because it's like, okay, I kind of get some of the pieces, but I think I cannot say that I do understand what the heck is going on.
Yeah, this is for the. Yeah, this is a really long algorithms. Yeah.
Oh, not so bad.
Yeah.
So maybe in the meanwhile, while I'm staring at this, Arman can ask his question.
Yeah, I on your last slide, slide 24, you had a condition on the equal norms of these theta star, right?
Yeah. We have to make these assumptions of this theta 1 star to theta H capital H star. These are all the same.
So my question to you is if I understood correctly what you displayed on the slide, is that under this assumption you have a polynomial algorithm, correct?
Yeah. Actually,
right. So then the natural question is that can you give an intuitive argument as to why you would think that if this condition were violated, you would still get a polynomial algorithm? Or is the equality of the norms essentially needed for analytical purposes, but has really no grounding in the structure of the problem?
Yeah, very good question. Yeah. Actually, why we think that actually if we violate this assumptions, there also exists algorithms. So actually, we tend to believe that this both structure action space is a very good structures in the space in the action space. So it can help us to do explorations no matter the radius of this theta the norm of the theta is. So actually, but actually our analysis here involves something about this grid search. That is, we have to use the grid to approximate this capital theta. Actually, this step is heavily depending on this space of the norm. This space of the norm of theta is not very large. So if we drop these assumptions, our algorithms will not work here. But actually, there may be possible some ways that we can circumvent this grid search, and because by just sampling according to more policies. Yeah, I think. Yeah, let me show you on these algorithms. Actually, as you can see that here we only consider this two policies. One is a pi 0, the other is pi hi. That is that we take the action I on this layer, action rho h ei on the layer h. So we only have two policies there, but we can suppose more policies. Like actually, we can also choose maybe 1/2 times rho h times ei. This is also give us some information about the the parameter space. So maybe we can aggregate that part of the information into our current information. And given this, we can maybe make an offset to this sum expected of sum of the radius. And if we actually if we cancels out this term, then actually our algorithms also works. So based on this, we tend to believe that actually maybe with some additional tricks, we can make this we can remove this assumption of theta h1 theta 1 star to a theta h star of the same norm.
Thank you. But if I remember correctly, what was on the slide, you had a finite number of elements whose norm was identical, right? Am I correct with this? Go back to 24.
You mean
Yeah,
this?
here. So if instead of having equality, isn't it always the case that there is a finite bound on these h quantities, and isn't that all that matters?
What do you mean by finite? Yeah, actually, this also works if we don't assume that they are of the same. But if we assume that maybe 2 times theta 1 star equals to 3 times theta 2 star and equals to maybe h times theta h star. This if we have these equations, our algorithms also works. If we have some maybe structures on this norm, no matter what this structure is, our algorithms can work for that.
All right, thank you.
Thank you.
All right, so I do have some questions yeah, I guess it's a question for the uniform part, which is kind of simpler and easier to understand. I think I did understand that, but I want to verify whether my understanding is correct. So there, I think that I came to the conclusion that actually, even for these convex sets and whatnot, it's not convexity that you need. What you need is that the action 0 is there, and then you can run an optimal design on the action set, and you should be able to push everything through. So the crucial assumption seems to be that, okay, you have the uniform action structure. That was pretty important in that part. And then in addition to that, that the action 0 is there. That's very crucial. And the rest of it, I don't know, because you're just trying to collect information in all possible directions, but you can do that for a lot of different sets. Actually, Kiefer Wolfowitz tells us that you don't have to query the orthogonal directions. You can query a bunch of directions, and then you will get the information you wanted.
Yeah, actually, I think that why we had to make this convex set assumption is that, yeah, actually, we agreed. I agree that actually, this pi 0 and pi hi, this is also important. But there's also another thing, which is in the line 9. Taking these actions, this is greedy actions with respect to the parameters we calculate. And actually, if we don't assume that this set is convex, so taking this greedy action,
just calculate it somewhere. It's like once you have the parameters, you assume that you have an optimization record that calculates it, calculate it.
Yeah, but yeah, if we can do this, but actually, if the set is not convex, so we don't have this guarantee. Like actually, this is the greedy actions of this parameters, and this is the greedy actions of that parameters. So we can bound this difference between this the reward of this this action and this actions by the norm of the difference of this two estimations of the parameters. We cannot do this. But if the set is convex, so we have these projections on the convex set. This nice properties, so we can have such a nice bound.
So basically, you say that in the analysis of the algorithm, somewhere the convexity assumption was used. I just didn't see it from the description of the algorithm.
Yeah,
but
it's not used in the line 6, 5, and 4, 5, and 6. Yeah, this exploration part actually doesn't use this convex assumption.
But so let me try to explain my thought process again, and then you will tell me where I'm going wrong. So my thought process was that if we knew theta star for each stage, we would be done.
Yeah.
Okay, so we are just trying to estimate theta star. And then you have these very beautiful algebraic relationships that tell us that you can estimate the inner product of theta h with any action in your action set. So after making these simplifying assumptions about the well, the assumption was that all action sets, like no matter what theta would be, oh, I see. It's like it should be all the same action sets. Like it doesn't matter where it's a ball or not. It's all the same action sets. Then you have the algebraic relations that you had, like this norm will be replaced by, like the induced norm of the corresponding action set. That's fine. And things are gonna cancel. And then for any inner product, you can estimate that by just running the policies. And then that gives you a way of estimating theta, like you solve linear equations. And Kiefer-Wolfowitz tells us that you don't have to, like, it doesn't matter what the set under which the linear equations you need to solve, you will get away with body samples.
Yeah, actually, one thing that this is this understanding is is almost correct.
Okay.
One thing that actually for these algorithms we use beyond this ball structure is that actually for all the states in the same layer, maybe in the layer H, actually the action set or the feature space of the action space, actually they are all similar to each other. Like actually, if this state actually the actions look like a ball, the other states the action space has to be looks like a ball. If this actions the feature space is a cube, the others also looks like a cube.
I agree.
Not like this is a ball, the other is a cube.
I agree. Yeah.
Not tractable.
Yeah. I agree with that.
Yeah.
But after that, like you don't have to have convexity or anything. Like I don't see how convexity is being used.
Yeah, actually, maybe this convexity is not useful. Yeah, but actually, for this greedy actions, taking the greedy action, this part actually think that with this convexity is more easier to analyze, because actually we can just directly bound the difference of the value functions, the difference between
Sure.
based on these actions, based on the difference between the difference between the parameters. But actually, without the convexity, actually this can look very weird, because actually, if we just change a little bit of this actions, change a little bit of this parameters, actually this still be a huge change in the
We don't care. We care about the values, and the values don't change that much.
Let me think. But the values
should be smooth.
Yeah, but actually one other thing which is also affects the accuracy is that actually the norm of this actions we take. Like actually, if we
sure, so there is this argument that was arguing that if rho h is small, it doesn't matter, blah blah blah. That should be worked out, and I wasn't quite sure whether that's going to work out if you try to generalize my way. But yeah, I'm not Yeah. Okay. Anyways, I think that like we can stop here. I kind of understand what you're saying, and I guess you understand what I'm saying.
Yeah.
Okay.
Yeah. I understand. Maybe this convexity is not
Like, really that crucial.
Yeah.
Okay. Yeah. Good.
Yeah. But actually, one thing that is necessary is that actually, for these algorithms to make it work, we have to we have to guarantee that we can explore at every directions. Like actually, if there's only two actions, so maybe if
Yeah, it's hyperbophile. It's just like you're spanning the space.
Yeah.
That's just spanning the space. It's
but actually only spanning this space might not be very good. Is that actually there's also maybe if there's very close to each other, like actually they're always of the very small angle, like actually they're all tend to stick to each other. So maybe there's
again, I'm going to refer to Kiefer-Wolfowitz that tells us that if we only care about estimating the linear function in a pointwise manner, it will not matter. If we only care about the values, will not matter.
Very good point. Yeah, I think that maybe in that case this is also doable. Yeah, but so actually based on this observation, so the most important thing is actually for every state, actually this feature space has to be looks like a similar thing.
Yeah, it's like kind of the same set.
Yeah, ball to ball, cube to cube, triangle to triangle, something.
Yeah. So all the feature space for any given action, they are identical to each other. They're just shifted around. Yeah.
Yes. Yeah. Exactly.
Yeah. Very cool. I cannot say I did understand the second more complicated algorithm, but maybe it just.
Yeah, actually, this second part, actually, one thing that I mentioned is about this this hierarchical exploration. But actually, this thing, actually, we can also remove this part. But actually, if we remove this part, if we remove this part, the final bound we get will be absolute to the seventh compared to this absolute cube. So actually, if we add this hierarchical exploration part, actually will drastically improve the rates.
That's nice.
Yeah, that's also one interesting point we think in this construction.